So we are discussing transistors at high frequency. Transistors means BJT. BJT at high frequency, and the model is hybrid pi model. This is not a qualitative discussion. We are only doing the quantitative part. So let's see what is hybrid pi model that depicts the functioning of a transistor, a BJT at high frequencies. Let's see. To understand it, let's say this is our PNP or NPN transistor. Okay, this is base, this is collector, this is emitter. What we have, there is a point B dash which is not accessible from outside. For the purpose of understanding the functioning of a transistor, this point is assumed. So this is one resistor, this is second, and this is third resistor. This is resistor RB-C. This is RB-E, and this is not here. This should be drawn inside the transistor. So this is here. This resistor. So this resistor is RBB dash. It is called the spreading resistor. And in some books you will find this RBB dash is called Rx. This RB dash E is called R pi, and RB dash C is called R mu. So you should remember both terminologies, because you may find this or this in your question. So this is clear. If we have a transistor, it is PNP or NPN, we can think of a point B dash inside the the middle portion, that is PNP, then this N part. This is an assumption. So this is B dash. So we have resistances, spreading resistances, that are RBB dash, here RB dash C and RB dash E. They are also called Rx, R pi and R mu. This is clear. Now let's see the hybrid pi model. We have seen the small signal H parameter model, H model. Now let's see hybrid pi model. It is like this. See, this is, we come to the point B dash, and I am doing this for C configuration only. So this is B, our base, and this is our B dash, the point that I just showed you. This is RBB dash. Okay, between this and this. This is easier to remember, but you should remember this also. This is Rx. Now, our emitter is common. Let's draw it. So here we have one resistor, that is RB-E. This is emitter. So this is RB-E, or what we call it, R pi. It is also denoted as R pi. Parallel to it is a capacitance, that is CE in this nomenclature, and in this nomenclature it is called C pi. Clear? Then from, let B dash be here only, from B dash to collector we have a capacitance. This is our collector. This is a capacitance which is called CC in this configuration, in this nomenclature, and in this pi nomenclature it is called C mu, and parallel to it is a resistor which is RB-C. RB-C, this is our collector node. So RB-C is basically R mu. Now here we have one resistor, that is RCE, or this is also denoted as RO in this pi nomenclature, and then we have one current source. This is a current source with GM and this voltage. See, this voltage. This voltage is VB dash E. So you can write VB dash E, or you can write it as GM V pi. This is the V pi voltage, V pi or VB dash E, whatever you like. This is collector and this is our emitter. This is hybrid pi model. So this is R pi hybrid pi model. Don't get confused by this complicated figure. If your circuit is like this, let's say this is common emitter configuration. I hope you are able to see this collector and this is emitter, and this is grounded, and we have a load here. How we put load? This is RL, this is VCC. Here we have RS and VS plus minus. This is grounded. This. So how to transform this circuit in this hybrid pi model? Nothing. This is the input part. You put RS and VS here. VS, RS. So this is your input now, and load is on the output collector side. So this is RL. It is so simple. Clear? Now what I am doing, I'll derive expressions for all these parameters. The first is transistor transconductance. You have to remember the names. What is it? GM. You saw GM V pi, that side GM V dash E. So this is this. The how to find GM is basically equal to IC mod of IC, that is the magnitude only, by VT. And what is VT? You know this very well, volt equivalent of temperature. VT, that is given by T by 11,600, where T is in Kelvin. Okay, so GM is mod of IC by VT. Remember it, write it somewhere. Now input conductance. Input conductance, it is GB dash E. And what is GB dash E? It is RB dash E. Clear? B dash E, that was pi. RB dash E is basically R pi. So remember this. And this GB dash E is given as GM by HFE. You know what is HFE? The forward transfer ratio in case of CE, common emitter. So this is GM by HFE. So RB dash E, that is R pi, is equal to just inverse of this, that is HFE by GM. What is GM? You know, I just told you GM. So GB dash E, RB dash E, R pi, this. So write it down. The feedback conductance. What is GB dash C? That is from B dash to the collector, and this is equal to RB dash C. And what is RB dash C? What we say, R mu. Now we have RB dash E equal to HRE into this RB dash C. This is one expression. Now this is HFE by GM. Okay, so from here what you get, RB dash C is equal to HFE by HRE into GM. You can use the term R mu also. So R mu is HFE by HRE GM. Practically this is a very large quantity, very big quantity, because see, this is RB dash C, B dash to this, and these two are practically disconnected. Therefore, if you will put the values, this is very high, almost open circuit. Okay. Now the base spreading resistance. This is our RBB dash. Between this we had this, and this RBB dash, this was B dash, this is B, this is E, and this was RB dash E, that is R pi, and this is Rx. Now this is basically, if you compare it with the H model, this is HIE, the input resistor. If you remember, this was the, we used to denote it like this, HIE, this was HRE into V output. So this is HIE. HIE is equal to RBB dash plus RB dash E, that is Rx plus R pi, HIE. So we can have values and you can find from this expression. Okay. Now the output conductance, that was in the output, it was GCE. Okay, that is 1 by RCE, or we had, I told you this is also given as RO. Now GCE, this output conductance, is almost equal to HOE minus GMHRE. Okay, so from here you can find RCE or RO, that is 1 by GCE, that is 1 by HOE minus GMHRE. So these are the 5 types of resistance or conductance that is found, that we find in hybrid pi model. Now we have 2 types of capacitances there. Capacitances. First is the C pi and second is C mu. This is basically given as CE and this is given as CC. This is also given as COB and is given by the manufacturer. In the data sheet you will find the value of COB for a particular transistor. And as far as this is concerned, CE, it is given as CDE plus CTE. This is the emitter diffusion capacitance and this is the emitter junction capacitance. Emitter diffusion capacitance and emitter junction capacitance. And one more thing, CE is experimentally, it has been found to be equal to GM by 2 pi FT. Remember this formula. What is FT? FT is the frequency at which the short circuit current gain for C is equal to 1. Short circuit current gain, that is output V, output is 0. This is equal to 1. The frequency at which the short circuit current gain is equal to 1 is called FT. So this has been used. CE is GM by 2 pi FT. One more important thing you should remember regarding FT is that all these parameters that we saw, they were independent of frequency. This is valid till this is less than 3 of FT. That is the operating frequency. When it is less than thrice of FT, we will have these parameters independent of frequency, that is R pi, R mu, everything. If this increases, then they'll change. The value will change with frequency. This you should keep in mind. Now let's see what is CE in common emitter short circuit current gain. So this is given as AI, this is given as minus HFE by 1 plus J of F by F beta. So this is now complex. This is because of frequency. What is F beta? F of beta is given as GB dash E by 2 pi CE plus CC. That is GB dash E. In the last page we had seen GB dash E was GM by HFE. So HFE into 2 pi C plus CC. And what is C and CC? C pi and C mu. So this can be written as Gm by 2 pi HFE C pi plus C mu. You must remember this formula. Now if you take mod of this value, that is the magnitude of this has magnitude and direction. So if you take magnitude, what it will be? This will be positive and this will be square and under root of this. You know this? We have one more expression that relates beta to HFE. So HFE is given as beta 0 by 1 plus J C pi plus C mu into R pi. This you should remember. This comes very handy in solving problems. And beta 0 is also given as Gm into R pi. So this is also a very important expression. So you should remember these two expressions also. Now let's see what is Ft. Ft is basically HFE into F beta, and so this is equal to Gm by 2 pi Ce plus Cc, or Gm by 2 pi C pi plus C mu. Okay, so we have a relation between Ft, HFE, F beta, Gm, C pi, C mu. Therefore, using that expression, we can write current gain as equal to minus HFE by 1 plus J HFE into F by Ft. Why? We have used the expression from there, HFE into F beta is equal to Ft. So, this can be used. And similarly, if you want the magnitude, this will be this plus this square and under root. So you can see the magnitude from here. At this will be equal to 1. Now all these expressions that we derived was current gain without the resistive load. What will be the current gain with resistive load RL? Now our F beta, when we take the load RL, this is denoted as FH, which is equal to G B dash E by 2 pi C. What is B dash E? This is 1 by R pi. So I am writing the expressions in pi nomenclature also. Okay, and C is given as CE plus C into 1 plus Gm RL. That is, this is CE. CE is what? C pi, and this is C mu 1 plus Gm RL. Okay, so we'll use these expressions to solve problems. Let's see some questions, see some numericals. Okay, so we have to find F beta and Ft. We have F beta from the expression, this is G B dash E by 2 pi C plus Cc, or C pi plus C mu. G B dash E, this is, we have been given 1 kilo ohm, so this will be 10 to the power minus 3 moles, this expression. Okay, so this is G B dash E by 2 pi into Ce. Ce is what? 1 picofarad, and C is 0.2. So this is 1 plus 0.2. So 1.2 picofarad. Pico is 10 to the power minus 12. Okay. So what we get? This will be 1 by 2 pi into 1.2. 10 to the power 12 goes here. This becomes 12 minus 3, 9. That is gigahertz. So this comes to 133 megahertz. Okay. Now let's see Ft. Ft is same. If you remember, it is same. It is just Gm by 2 pi C plus Cc. So let this remain same. This is 10 to the power minus 3. No, not. We'll see what is Gm. This is 2 pi. What is Gm? Gm is 50 into milli. So 10 to the power minus 3. Now, what do we have? So it comes to 6.631 gigahertz. That is 10 to the power 9 hertz. Clear? So the second question is, we have the same figures, only load resistor has been introduced. What we have to find is FH. What is FH? So we know that FH is equal to GB dash E by 2 pi C, where C is what? CE plus CC into 1 plus GM RL. So let's put the value. CE is 1 picofarad. 1, let's say we'll use pico in the last, plus 0.2 into 1 plus GM. GM is 50 milli. 50 into 10 to the power minus 3 into RL. RL is 2K. So 2 into 10 to the power 3. This is picofarads. What is this? Say, this cancels. So this is 15 to 200. So 101 into 0.2. So this will be 101 into 0.2, 20.2 plus 1. So this is 21.2 picofarad. So now we put it here. This is GB dash is 1, that is 10 to the power minus 3. This is R, this is G. So this is inverse of this. 2 pi into this, 21.2 into 10 to the power minus 12. I am writing it here, plus 12. So this comes to, this will come to 7.5 megahertz. Okay.